How to create shear force and bending moment diagram of frame element using finite element method. There are two elements. Element 1 is inclined connecting nodes 1 and 2, and element 2 is horizontal connecting nodes 2 and 3. The global axis is denoted as x in horizontal direction and y in vertical direction. Element 1 is inclined at an angle 45 degree to the horizontal, while the element 2 is parallel to global coordinate x-axis. Element 2 has UDL of 1000 pounds per feet acting downward, which generates force and moment at node 2 and 3. Since the force is uniform throughout the length, a point load of W into L can be assumed to act at the center, which gives the nodal forces at node 2 and 3 as WL by 2, that is 1000 by 2, which is 500 pounds acting in vertical downward direction, as the load is applied at the center of the element 2. The uniformly distributed load acting throughout the beam is converted into nodal forces at node 2 and node 3. The sign convention is taken as force is positive in upward and forward direction, while the moment is positive in anti-clockwise direction. Similarly, the fixing moment is WL square by 12, where W is UDL load and L is 40 feet. Correction note: the fixing moment for node 2 is negative as the central load causes clockwise rotation, while for node 3 the moment is in clockwise direction and hence taken as positive as per our sign convention. This will be corrected in later part of the video. Now moving on to determination of stiffness matrix and transformation matrix of frame elements. For node 1, the angle of inclination is at 45 degree, taking cosine and sine of angle in radian. When the frame elements are not aligned to global coordinate axis, we have to use transformation matrix to convert the local coordinate to global coordinate system. The local stiffness matrix is to be converted to global stiffness matrix. The C represents cosine, while S represents sine value. This first block is for element 1, where there is transformation required for both x direction movement and y direction movement. But there is no transformation for z direction, which is out of screen, as z direction of local coordinate system is parallel to z direction of global coordinate system. All other elements are 0 in this transformation matrix. Correction note: the sign term in cell D22 and G32 should be positive, while the sign term in C30 and F33 should be negative. Now moving on to stiffness matrix. AE by L represents the linear stiffness component for movement in x direction for for both nodes. X, Y and theta represents the stiffness component of nodes at horizontal, vertical and Z direction. The values of 12 EI, 6 EIL, 4 EIL square represents transverse and rotational movement. Make sure to use right notation for positive and negative values and position of each of the elements. Now making this value look like matrix by inserting a bracket on both left and right hand side. The correction notes to keep in mind: signs of sine and cosine term in transformation matrix, signs and component of local stiffness matrix. This ends part 1 of how to create shear force and bending moment diagram of frame element using finite element method.